All right. It's my great pleasure to have Engin Kirda here from Northeastern. So he's usually sitting over there, so you can see his office from here, so not too far. But yeah, so he's been doing a lot of work in system security, web security, early malware analysis work, and so on. He's currently chairing CCS, which is one of the big security conferences, and a bunch of other things. And so he'll present the recent work on security implications of conversion anomalies in different versions of HTTP.
So thanks a lot for the invite. Thanks a lot for the intro, Gianluca. So it's a pleasure to be here. As Gianluca just pointed out, I can actually see my portrait from here. Very, very interesting. Very nice to meet you guys out here. So I am going to be talking about a system we built maybe 1.5 years ago. It's called FRAMESHIFTER. And I'll be talking about a specific class of vulnerability that I personally find interesting because they have been known for a while, but they became kind of relevant again quite recently. So I'll be talking about what these vulnerabilities are. I'll talk about the system we developed to measure them and to try to understand what's actually happening on the internet. As Gianluca said, in general, I'm interested in system security for all sorts of topics. If it's practical, typically there are no formulas in it because I'm not smart enough for formulas. You get interested in that. Lately, I've been focusing on main areas. One of them has been embedded system security and fuzzing. So there's been some recent work in that domain, but I've always been interested in web security. And when my students came up with these areas and they said, hey, this is actually looks interesting, we'd like to work on this, I was skeptical at first because I thought, hey, this is actually nothing super new, but it ended up in a number of papers. So I just selected one, which is a Usenix paper, I'm going to be talking about. So my talk today is going to be about the general problem of conversion anomalies. So these issues happen when you have two different systems that have been implemented independently. So they by themselves are secure, but when you start combining them, that ends up leading to interesting security problems, right? So discrepancies in the implementations and the way they interpret, right? So a result of this can be a problem such as HTTP request smuggling. People call it HRS, and I'll show you what HRS actually is. This is not something that just got, that just popped up a few years ago. This is something that people knew for quite a while, but it became relevant again just because of the way the internet has developed. This is because of the way it's serving content. So I will briefly explain HRS and I'll provide some background context and I'll talk about the system that my students work on. So I'll be focusing on this very specific issue. And industry is right now actively looking for solutions to this specific issue. We're working on more papers, and interestingly, it's not a very super easy problem to solve. So right now, I don't know of many solutions out there, right? But if you go and talk to companies, they'll be telling you that if you come up with a solution to some of these issues, they'll be very, very happy to hear about it. So the work I'm presenting was led by my PhD students, or former PhD students, Behruz Jabiev, current PhD student Steve Sprecher, current PhD student Anthony Gavazian from Atlantic. And it was co-led and mainly directed by my former student, Kaan Omarlıoğlu at Akamai. So he's been working there. His contribution to this work was very essential. He's the CDN expert. So, I was basically lucky enough to be involved. So I'm basically presenting their work, right? So this is what professors typically do. But they're the smart people. They actually came up with all the algorithms and things like that. It's a pleasure to present their work. So the paper appeared at Usenix Security in 2022. There's been follow-up work since then. If you actually look for this paper online, you can download it. All the details are there. I'll be talking about some of the attacks. The attack details are there as well. If you have any questions, you can ask me. If I can't answer it, then I'm happy to forward them to some of the students who actually worked on some of these concrete attacks. So what is HTTP request smuggling, right? If you look at the history, HRS has been around for quite a while now, this specific issue. It was first discovered in 2005. And I remember when I was teaching security back then, some people, I heard about HRS, I looked into it. I had one slide in my classes on HRS, but I didn't really take it seriously because it was actually not a huge thing. It was like a, corner case type of vulnerability. It didn't impact too many people. So it was kind of interesting, but nothing to worry about at the time, right? It has, though, started to gain attention quite recently, right? James Kettle, It's well known in the security domain. If you know the Burp toolkit that you can use to do web security, right? He's the author of that. He gave a black hat talk in 2019. And he sort of rediscovered this issue, right? He started looking into HRS and he said, hey, you know, there are actually interesting bugs here and you can exploit them, right? So he sort of picked this up again. And lately, if you look at the work, the non-scientific work, it has mainly been on transfer encoding versus transfer length discrepancies. So these two headers that you have in HTTP, what happens if you start misusing them, right? People have specifically looked at that, but nobody had really looked into this more systematically. Right? So in the first work that we did, that we published at CCS a while back, we said, okay, let's look at this systematically, and we were able to show that these issues actually occur not just for these headers, but these are just like more general problems. In any case, HRS, is it important? Yes, it is, but because if you look into CVEs and how people are making bug bounty money, you're actually going to see that people are able to find vulnerabilities that are HRS. They're able to exploit them. They're able to sell them. You know, sometimes they make well over $70,000 in bug bounties for finding these specific issues, right? So companies like Akamai, Cloudflare, all these content distribution networks are kind of interested in this, right? So it is a real thing, right? It's not just theory. But what is it, right? So if you look at the HTTP request anatomy, right? If you go to DuckDuckGo or you go to google.com and you type in funny cats, what happens, right? Your browser would convert this to an HTTP request, right? And the request might look something like this. It says get/HTTP 1.1. You have some headers. You have the content length, which is 16. And you have the data, which is this query string that you've typed, right? And this would then be forwarded, right? But in any case, you have the request line, you have the request body, and you have the request headers, and you have the request body. So all these things will be taken, will be sent to the server will process it, and it will respond back to you, right? Another way of displaying this request would be by using transfer encoding. This is the web, this is HTTP, so that there are different ways of representing information. You don't have to use content length. You could also create the same request using transfer encoding, say chunked encoding, and use HTTP to send this request that looks different, but is exactly semantically the same, right? These are equal. So content length versus transfer encoding. So this is the first thing people actually looked at. They were like, okay, you have these two different headers. What would happen actually if you start combining them? What would happen if I actually create a request where I say transfer encoding is chunked? I also say content length is 16, right? What happens now totally depends on your implementation, right? So you have a server that has implemented HTTP. How does a server react if it sees these two headers, right? Does it take the first one and deal with it? Does it take the second one? Does it take both of them, or does it generate an error message just because this is not a valid HTTP request, right?
In the official HTTP standard, what would be the right behavior? Is undefined?
Excellent question. It's undefined, right? So, you know, it's a very detailed specification, but it's very difficult to specify everything in detail. And this is the reason why some of these issues are coming up, just because it's up to you, right? You deal with it pretty much.
Errors.
Right. Typically, you would have to do an error, but sometimes people might just ignore it and, you know, the errors.
Should default to one of the two.
Exactly. You default to one or the second one. So if I take a request like this, right? Transfer encoding is chunk, content length is 16, and I add a bunch of A's, right? A classic security testing string, right? At the end of that request. And suppose I have a setup now that we find on the internet very often where I'm using proxies. So I'm not just sending this directly to the server, but I'm sending it to, say, Akamai, that is my proxy. And my proxy processes that and then forwards it to the origin server, right? So I have the setup where I have the reverse proxy and the origin. The problem now is that you have two different implementations, right? The reverse proxy takes this, and because it's not really well defined, you know, ideally it should generate an error, but maybe it doesn't, right? It might decide to deal with the second header. It ignores the first one. It says content length is 64, right? And that packet is processed and then forwarded to the origin server, right? But it's actually looking at the content length. So this gets forwarded, and the origin server has been implemented differently. So what it does is it actually decides to look at the transfer encoding and doesn't look at the second part, just because of the way it's been implemented. By using these discrepancies, people have actually demonstrated that you can then smuggle, or you can insert extra characters or packets, and you can sort of forward them to a target server, right? So these A's actually end up going to the origin server. What does the origin server now do? Well, this could be a meaningful thing, or it could be a non-meaningful thing. But if it actually looks at the AAAs, maybe it thinks it's not a valid HTTP request, and simply it would generate an error. So it's just failed, right? This would be the simplest case. Nothing really bad has happened, but it's not a good thing, right? Basically just failed. So yes, you have a bunch of A's. Typically, this would generate an error message because it's not a valid HTTP request, right? So if you take a request like this, right? The first request is AAA. You're on the same connection, and this is a reverse proxy and an origin. So lots of requests are coming, they're being forwarded. The next one might end up being a valid request, right? Mm-hmm. It also ends up on the origin server, but now you sort of brought the system out of sync. You have a bunch of A's here, that's not a valid HTTP request, then you have a valid HTTP request. So this origin server now doesn't really know what to do, right? The second one it can deal with. The first request is just a meaningless request, right? So that request has been smuggled in. That's why people call it HTTP request smuggling. And this would then, likely generate an error message. But instead of the AAAs, what happens if I actually insert a real request, right? Instead of AAA, I say, get/abc google.com. Now I've managed to, without these proxies or these servers realizing, I managed to inject an extra request, right, that they're not aware of, that actually ends up going to the origin, right? It's a valid request. And people have looked at this and they said, okay, how can we actually make use of this? Well, you can do a bunch of things they've demonstrated. So the attacks are things like response queue poisoning. For example, you have the same setup, right? You're sending all these requests to the proxy, they're being forwarded. But if I can smuggle extra packets, I can actually inject this extra packet. So the response queue is poisoned. So you're looking for Google, but I send you the CNN pages or something, right? So everything is out of sync. This is the simplest thing I can do, right? So somebody goes to BU, but suddenly they see the Northeastern page because I actually brought all these requests out of sync. So that's one thing I can do, right? Another thing that people have demonstrated is web cache poisoning. This is worse because all these proxies actually have caches, but I can poison your cache, right? So every time you go to bu.com, not com, edu, but universities like businesses today are exactly wrong. edu, right? So I can actually poison it, so you might end up going to Northeastern, right? Or things like that, right? People have demonstrated that as well. That's a problem. So you have all these requests, and the mapping is something I can play around with. Question?
But wouldn't the HTTPS certification fail then on the content?
So in this case, I think the HTTP the certification does not fail because of the proxy, right? It's the proxy is fetching it.
Oh, you're using the proxy.
Exactly. So in this setup, stuff gets a bit more complicated. One other thing people have demonstrated is bypassing the security controls, right? So if you are actually looking at these requests, you have a web firewall. They're very popular today. Everyone has that as well, right? All organizations have some sort of a firewall, Palo Alto, etc. You're looking at these requests. Well, if I'm able to smuggle these extra requests, right? Maybe you totally miss it. You're not supposed to maybe access a URL, but I'm able to inject it to you. So you bypass the security controls, which would be bad, right? So you're actually using HRS to bypass the firewall. Okay. So all of these things are bad. People have demonstrated them, and this is a basic problem of these discrepancy models, right? So we looked at that, and there's a paper that we published where we actually found lots and lots of vulnerabilities. We contacted many people. There's an open source tool that we developed, and this tool can be used. It's called T-Rex to find all these issues automatically, right? And some companies were internally even using them, right? So what we had looked at was HTTP1 though. So all of that I discussed is the HTTP1 protocol, very, very popular. However, the web has been moving to HTTP2, right, for a number of different reasons. And HTTP2 is supposed to be more efficient. It's been done because it's more compressed, etc. So there are reasons. I think 60–70% of the websites are actually using that, right? If you actually send out a request today, there's a higher chance that it's going to be HTTP2 rather than what I just talked about, HTTP1. So if you look, so this is pretty much the HTTP1 request, right? So this is something we looked at. So why did they do that? There's this thing called head of line blocking. People realize, if you have lots of headers, everything is being done over the same connection. Setting up the connection takes a lot of time. It's not that efficient, right? So with this new protocol, things are much more efficient. And if you have things like repeating headers, you have one stream, and it's an optimized protocol. You can send everything over this one stream. And servers today can actually deal with this. Proxies today can actually also deal with this. So HTTP2 basically optimizes everything, right? So you have headers, you have these packets called continuation. So if you have even more headers that you'd like to send, right, you can just send more packets containing these headers. And at the end, you have the data, but this is all a stream. You're putting all these packets on the same line. And if you have more data coming up, you can start creating more packets and you start forward. So that's HTTP2. So they're useful. There are more packets if you actually look at the specification, quite complicated, of course. But this is the main idea of HTTP2. So you have headers, just like HTTP1, but they have these things called continuation packets, and then you have data packets as well. If you look at content length transfer encoding, these are the same, right? It's like HTTP1, but the protocol has been altered. Okay, so if I send a packet to the origin, there's a good chance that it's going to be in HTTP2, and it's going to respond back to me in HTTP2, right? It turns out, though, that if you have a reverse proxy, like we do on the internet today, where you have companies like Cloudflare and Akamai, the reverse proxy might support HTTP2, but when it forwards the packets, it actually converts them to HTTP1, and so it doesn't actually use HTTP2 all the way, right? The question is why. So interestingly, nobody really knows why, and that's the truth. The reality is probably because of performance. They probably think, why would we use HTTP2? We don't need it, so they haven't actually implemented it. But in any case, of the 10 technologies that we looked at while doing this work, we saw that 9 of them were doing this. One of them is actually continuing everything in HTTP2, right? But the rest actually were not, right? So I'm sure they have their reasons, but this actually opens up an interesting question now. What happens if you're converting these HTTP2 requests to HTTP1 and they're being forwarded? Does that lead to any security problem, right? So this is basically what we wanted to find out in this work, right? So it arrives at the reverse proxy in HTTP2, all is good, but then we converted to HTTP1, we forwarded to the origin. Well, there can be discrepancies here as well, right? Or can there be, right? This is something that we want to
But then the reverse proxy has to kind of store and forward the multi-packet.
Exactly, it actually does all of that. So they actually have algorithms and they have code that does the conversion. So again, why do they do this? Compatibility and performance reasons, probably legacy systems, right? They're all these huge setups. But if you're just directly dealing with Apple, you're good. But if you actually have Akamai in between, which is the case today, right? Then this conversion seems to be happening a lot, right? So as I said, no support for HTTP2 to upstream in 9 out of 10 technologies that we looked at. I looked at 10 very popular technologies like Nginx, etc. They actually were not supported. Yeah.
So if it is about performance, then won't the performance be bad in case we are doing this conversion? Because there will be head of line blocking,
Right.
we will be waiting.
Excellent question. Could be, but I don't know. Right? So even the former student I had, the postdoc, he doesn't know, right? This is what they do. Nobody knows why they do it. But when we first found out, we thought, okay, it's kind of interesting. It's not something a lot of people have thought about.
I think I know why they do it, because the first one did it.
Exactly. In any case, he confirmed this in experiments, right? It's like a surprising finding. And then scientifically, you ask yourself, okay, wow, can we do something with this, right? Maybe we should look into this. So the research goal was to investigate the anomalies in the conversion process and their security implications. So we thought, okay, can we actually develop a tool that targets this conversion process packets are forwarded, and then that might lead to HRS or not, or maybe other attacks, right? This is something that we actually want to find out. So past research on conversion anomalies did exist, not scientifically, but people have looked at this, in like very specific cases or in the context of HTTP request smuggling, right? They looked at this and they found out, hey, okay, this is possible, attacks are possible, so we knew this, but they didn't actually systematically look at many technologies and look at this more scientific, right? So request body parsing was at the root of the recent HTTP attacks that people have looked at. So in this research, we are focusing on body-related conversion anomalies that nobody had looked at. So we look at everything, including these headers, but including the body as well, right? Can we actually play around with the entire packet and make it lead to some conversion anomaly? And if it does, what does that actually mean, right? Can that actually lead to a security problem? This is something we wanted to understand. So we're not looking for a specific type of anomaly or attack. That's how we started. If you find other issues, great. We'll just report them and then we'll show people what is actually possible in practice, right? So availability and ethics was important. So FRAMESHIFTER is an open source tool. It's available, so you can download it, just like the other things we had done in this space. And we conducted the study in a very controlled environment. So if you're actually looking and you're doing work like this, of course, you can't just start attacking Apple, sending packets and smuggling things, right? That's not possible. So you need to create a local environment. When you forward packets, they have to be your packets. You can then analyze them, you can find bugs, but you can't do this against real websites. So we made sure this was not the case. So we're not launching any attacks against external entities. We performed full responsible disclosure to all tech vendors. So every time we found a vulnerability, before the paper actually appeared, we contacted them. The students actually wrote up the paper. They emailed them to the parties. We actually got feedback as well, right? People told us this is true, this is not, etc. So the copy of the paper and the data was provided to all affected parties, the code as well, right? Which actually ended up being quite useful. So what is FRAMESHIFTER? FRAMESHIFTER is an HTTP2 fuzzer, right? So in the first work that we had done, we were doing fuzzing on the web, so randomly generating packets, etc., based on some algorithms, trying to make it lead to these discrepancies, right? In this case, we're actually focusing on HTTP2. So we're generating HTTP2 inputs. So you have, you know exactly how the HTTP packets are created, right? So I can take this, I can feed it into an algorithm, and I know exactly where the headers are, so I can play around with that. I can do things like double the headers, right? What happens if I send content length twice, right? What happens if I put on integer value for content length? Does that lead to an issue, right? All of these things you can put into an algorithm. And based on that, you can generate inputs, random inputs. You feed it to these systems, and then the rest is, okay, you try to observe and see what actually happens, right? By comparison. So this was the basic premise, right? So we created a mutation engine, right, for HTTP2 for these frame sequences. So you have HTTP2, as I showed you, right? So, in the headers, you can have maybe a post there, you have content length 16, you have query string, right? But I can start playing around with these, right? So instead of doing a post, what happens if I put a \t there, a tab, right? Or a \n, right? Does that lead to an issue? So I can take the content length and put an underscore there. Okay, what is that going to happen now, right? Is that, is the server going to process this? Is this going to lead to an error or not? Or I can make the content length 1, although the content is more than 1, right? Does that lead to a problem? Maybe the last part is not forward, right? So we do all of these, right? So we can generate all these inputs randomly, and then we feed it to these systems. The first step will be to record it and find out what's actually happening. So of course, we can then generate even more headers, etc., right? This is done automatically. Typically, we run this system for a couple of days, right? We have these servers, they generate all the input, and then at some point we collect the data, and the data needs to be analyzed, right? So in the experiments,
How do you make sure that these are independent trials? Do you restart the server every time? Because you may have impacted the state of the server with the previous packet now.
yeah, randomly. So, the idea here is to generate as many inputs as possible, as you'll see later, and we just record them. We know exactly what the inputs are, and we start comparing. So, it's systematic, but it's not exact or precise. Because the idea is to try to find any bugs that we can, classic fuzzy. So HTTP is sent, HTTP2 is sent to the target server that we actually set up. We make it convert things to HTTP1, right? And we do this for a bunch of popular technologies like Apache, Nginx, Caddy, ATS, HA proxy, Varnish, etc. Right? All of these are very popular tools, right? Proxies that are actually being used in practice. People use them, companies use them as well. So we took them, and the idea was, okay, let's do this for all of these technologies, see what we actually get, right? Generate inputs, and then Akamai, Cloudflare, etc. are the companies that we tested as well, right?
How do you test against Akamai? I mean, don't you have
So
to go
we
over that?
yes, but we make them forward package to our server. So we set up, packets are sent to Akamai. All that they do is they just actually analyze, they forward it, and the forwarded packet, if it contains an attack, comes to the server that we're hosting. So we're attacking ourselves pretty
If
much.
you poison the server, the Akamai server, it could affect other people's flows too. No?
But we have our own instance, so it's not like the entire Akamai services are being affected. So they set up an instance for us.
Oh, they did?
Exactly.
Oh, wow.
No, for all of them, right? So if you buy that, they basically not. So basically, they're hosting it for you. And in Akamai specifically, when we did these experiments, the former postdoc
Yeah, right.
had access, right? That was very helpful. So for the experiments, we pretty much have the input grammar, right? You're generating lots of random inputs. These HTTP2 inputs, we mutate them as much as we can, right? These mutated inputs, we forward them to the servers that we actually, or we send them to the servers that we've set up, like Apache, Varnish, etc. They downgrade these requests to HTTP1. They forward them to a TCP socket server, right? Which then takes these and we just write them into a database or a repository. So as a first step, all that we're actually doing is generating lots of inputs, and we're just generating these inputs. We're looking at how these technologies forward them, and we log them. Why is that useful? Well, now for a very specific input, I can see how Apache dealt with it, and I can also check how, say, Varnish dealt with it, right? I can see if there's actually discrepancy. Are they doing the same thing, or are they completely dealing with this in a different way, right? So we did this. We started then comparing, etc., and trying to identify different anomalies and vulnerabilities. So the anomalies, the type of things we saw was, if you take the content length, you make it 15, right? That would be an anomaly. Or these are the mutations, right? So if there's a 5 and I put an ampersand at the end, not a valid request, right? What would happen then? Would that create an issue? As I mentioned, that's a classic insecurity in general, especially on the web, where you double the headers, right? You see lots of security issues, hacking, where this simple idea of just doubling the headers can actually lead to, right? What we're doing as well here, content length is 5, content length is 10. What happens then? Right? How does the server deal actually with this, right? Or what happens if I write chunked and chunked twice, right? Obviously an error, but maybe this converts to suddenly content length, or this, this generates an error, or it doesn't, it just forwards it as is, right? These are the type of things that we actually want to see. So when you then take all these results that you collected, right? You've done a run for several days, you collected lots of data, and you start comparing these technologies. And in the paper, all these different anomalies are actually described. So if you want to take a closer look, you can download the paper. But there's a thing like invalid header value or invalid header termination. So you put the header, but you don't terminate it, right? And you compare these technologies. So you start comparing Apache with, say, HA proxy, right? For the different types of inputs, erroneous inputs that you've actually generated. And you can then start, in a graph like this, you can start seeing if they're diverging in behavior. If they are, that's actually a good sign for you as an attacker, because that's the first thing you're looking at, right? If they are dealing with the request in the same way, they both generate an error, I ignore that. But if one of them accepts it and forwards it, the other one does something different with it, well, that's kind of interesting, right? So this combination or this comparison of technologies at first, as a first step, is useful, because then it helps you identify what actually happens between different technologies, right? So what kind of attacks did we see, right? So we actually looked at this, we found some promising candidates. A lot of the cases we actually manually verified that there were some issues, right? So what kind of attacks? Well, one attack, I think I have 3 examples here, but we have like 5 of them, was a denial of servers. So in some cases, if lots of packets are being forwarded and you're able to do this trick, right, by providing different inputs, the reverse proxy forwards everything to the origin. The connection ends up sort of being taken, it's not terminated. And after a while, all these connections were full, right? So any more requests were then completely, so they did not work and the server was just blocking, right? This was one very concrete attack we saw. So for some technologies, just by doing this, just by doing the mutation, finding these right packet, you were able to just bring down the entire proxy, right? Just by sending this, it just blocks, right? Yeah.
Can you do that? I mean, since you're converting 2 to 1, if you just do a stream and you never close it, you're gonna have the same kind of effect, right?
You could, but you would assume that if a stream is not closed, it has a timeout. So it actually, at some point, the server would optimize that, right? I would assume that that's a case where the client crashes. But in this case, they're not able to deal with it because it just looks legit. Something happens.
So they don't have a timeout.
Exactly. So for request blackholing, it was a similar attack that we actually discovered where you do these anomalies, right? You find the right packets, and if you're able to inject or like smuggle these extra packets, so the initial requests are out of sync. So the first part is ignored. The second part is like a completely random type of request that actually comes in. So one part of the request gets ignored, it gets dropped, and the other one just generates an error, right? So you can do things like that where you're able to generate an error, although the request is sort of like legitimate, just by sort of like HRS request smuggling, you're able to make the servers ignore some of these requests, right? That was request blackholing. Another one was query of death. So there was one server that we actually identified where we were able to create a packet. When forwarded, it just brought down the entire server, right? Just one single packet, like the ping of death, that actually worked for some of these popular technologies. And why did we find it? We found it because of the system we were using, right? We found this automatically, so that was pretty cool. And of course, request smuggling. So the initial issue I discovered, I talked about, right? We wanted to see if this is actually possible, and we found a number of cases where request smuggling was also possible in conversions from HTTP 2 to HTTP 1, right? So that was also something that did occur, right? So where you're able to inject these extra packets, which means that you can do things like cache poisoning, you can do things like bypassing firewalls, right? Just because of this conversion issue, and you're able to do this automatically just by doing lots of experiments. So we also wanted to find out, okay, right, but what are the affected server pairs, right? So just because I find these discrepancies doesn't mean that every time I combine Apache and Nginx, it's going to lead to something. We wanted to actually find out what are the server pairs that are actually more vulnerable, right? So we mapped it out. So there's more data in the paper about this as well. But you can easily map out, if you combine Apache with, say, Cloudflare, does that lead to issues, right? Is that actually a high risk? Or is Apache combined with HA proxy? What kind of issues can that lead to, right? So you can actually do this by analyzing all this data and you can map it out. Because just because I found a discrepancy doesn't mean that it's a valid issue in the real world. This combination needs to make sense, right? And it has to be a real combination. Maybe Apache and Nginx is never combined, right? So this is something we want to find out, and we actually did measure that as well. And we also looked at, what kind of attacks affected what technology, right? You see that Caddy sort of comes out here looking not great, so they had a bunch of issues. And I think the ping of death issue was something that they also faced. So we did disclose all the issues that we found. So CVEs were assigned. Apache also assigned a CVE for some of the issues that we found. Varnish confirmed some of the issues that we actually reported to them. And Akamai, because we had good connections to them, started the remediation efforts, right? So they were actually very happy with the results. It ended up improving their systems as well, right? So what are the limitations of this work? So fuzz testing is primarily a testing approach. So it's not exhaustive, right? So it's not something that you can, where I can say, I ran it for a day and I found all the bugs. The longer you run it, the more you find, or maybe if the bugs are deeper, maybe you don't find them. So there's no guarantee. But that's the fundamental limitation of all fuzzing approaches. It's like a general issue. So the attacks we presented are realistic in the real world, and we actually showed it. You were able to exploit some of this stuff. But they will be impacted by various factors such as proxy configurations, security products that block connections, etc. So we had a lab environment, right? Maybe the proxy configuration we were using, maybe it wasn't super realistic, right? We took default configurations, but maybe somebody's locking down that server. So some attacks that we report might not happen in a very specific setting, who knows, right? But this is not a limitation of the work, right? So for at least for the settings that we tested, we did find the issues. So takeaways, open source HTTP2 fuzzer is the system that we created. It's available. We tried to systematically approach this to study conversion anomalies. We found some novel attack vectors, and we worked with vendors for the mitigation for this. And system-level attacks are rapidly taking over more traditional exploitation vectors. So your standard XSS is still a problem, right? XSS, cross-site scripting, you go to websites, you still find them, although people find them less, exciting these days. But these type of attacks that I talked about are getting more popular, not because they're super novel, it's just because you just have these systems deployed more and more. Content distribution systems today are a reality, right? You have big companies like Akamai, and it's often not the case that you directly go to a company and get their web page. You're getting them through different proxies, which means that there are definitely implementations, right? So the vulnerabilities depend on the exact technology combinations, their designs and implementation specifics, which makes this kind of difficult to fix. It's not easy, right? So I might test everything, but maybe I haven't tested Apache combined with Nginx. That might be issues, right? Not super easy. So identifying protocol conversion vulnerabilities and assessing their impact isn't actually as straightforward when you're analyzing systems in a bubble. We made a first attempt to make this more systematic. We created a tool, but there's definitely more things you can do here, and probably more things you need to do here to make this more exhaustive and have better coverage. So doing this at scale is still an open research problem, right? Also, lately, especially this year, we also looked at things like how do you find out what tech combinations are being used, right? We came up with a fingerprinting approach that allows us to see on the web, if I'm going through Akamai to say Apple, what is Apache Apple using, right? It's a proxy, but if I can identify these tech combinations, it means that I can then use an attack tool like this, right? So helps you defend, but also helps you attack, right? So it's a double edge. So anomalies could be minimized with guidance from the relevant protocol specifications. So you can standardize certain things. There's room for significant improvement in this space. And I think we're probably going to hear more and more of this as, as we have more deployments, more content is being served on the internet, right, using these technologies. All right, that's it. Happy to answer any questions.
Questions? What are questions?
Yes.
Sorry.
Yeah, I can
Yeah.
answer this. So have you worked with HTTP3 as well?
No. So that would be the next logical step if you want a paper, right? So you start looking at HTTP3. But people might say this is incremental, so I don't know. But we haven't. But
In case of HTTP3, this would be very difficult to even analyze because everything will be encrypted. You won't be able to see much.
Yeah, so definitely, yeah. So that would be the next logical step. I'm sure there are probably things there as well. Another question would be, is it only HTTP3 does it get converted? Who knows what's happening on the web in the real world? Yes.
So it seems to me that the root of the problem here is that when we're sending something to a proxy, there is no or very limited amounts of input sanitation. Just the proxy accepts everything, converts the protocol. It doesn't really care about if the content is valid or not. So to me, this was very enlightening because we need to do what we do to limit cross-site scripting at an HTTP level.
Yeah. So to summarize, you bring up the point saying, okay, there are lots of input validation issues as well, right? and you're right. Having a double, header is an input validation problem, right? Ideally, if I actually detect this, I should generate an error. I shouldn't process it. But these are so complex protocols, implementations are so complex that people sometimes think, what's the harm? You just pick the first one, ignore the second, right? Similar to some other, and this leads to other web issues as well, like, HTTP parameter pollutioning is exactly the same thing where you have these double headers and then you start injecting packets. But you're right, so ideally, this should be done. In practice, different complexity.
Yeah.
But I agree with you. So, there's something you can definitely do. When I teach security, I always say, you should always check if a parameter is provided twice because it never should be, right? Or the delimiter, right? It can always be a problem. So, if the content length is 16, maybe make sure it's an integer. Don't make sure that somebody can write an ampersand, right? I completely agree.
I think it's also a usability problem because I think there are actually a lot of software out there that actually has incorrect HTTP
Implementation,
implementation.
Yeah.
And once you start shutting it down,
Okay.
now things stop working, people get upset.
Yeah, I agree. I think it's similar to HTTP parsers, right? They're very fault tolerant, terrible for security, but good for usability.
Exactly.
But otherwise, the website doesn't work because you forgot a slash, right? Nobody wants that. It becomes tolerant, but then it leads to issues. Is exactly the reason why we have, JavaScript issues. They made it extremely fault tolerant, error tolerant, leading to all these security problems now. Not sure if it's easily solvable, but yeah, I agree. It's a trade-off. Yeah.
So in your experiments, did you also have a control reference setup where there was no protocol conversion? I'm assuming that's how you know that the protocol conversion is the actual culprit here for all the
We
issues.
configure these, so you mean to test if the conversion was happening or not?
No, if the conversion was the actual source of the problem.
So in this case, the conversion always was because of our setup, right? So we send the packet, it is being converted. We send an HTTP2 packet or like request. What we get back is HTTP1, so we know it's being converted, right? And we don't need to have a control request of any kind because we're just interested in seeing how different requests are handled. I can just send a random request to two servers and I want to see if they're different. If they're not different, I ignore it. But if there's a difference here, then I'm interested. Why is it different? Then I can start looking into what that can mean. Yeah.
I wanted to ask.
I'll wait.
So I'm thinking, right, so forgetting for a second about the fact that it's important to have fault tolerance, right? But it seems to me that if we really wanted to take a serious stab at this, we should use a bit of a programming language approach because, all right, so it's kind of like you want to create almost like a compiler of the request, and if the compiler rejects the request and is not conforming with the grammar, right? You already have a grammar, so in theory, you could do the other, the matching on the other side, right?
I think other things you can do, very difficult to do, but if you actually generate a model, say from the source code, and then you compare the models, because and then you can start seeing differences more maybe systematically, right? Because of the implementation. If there's a way of comparing the implementation rather than generating random requests, right? Very difficult stuff, but you're right. I think something more deeper needs to be done, maybe or maybe take the HTTP specifications, parse it in some way and find out which parts are unclear or something. I don't know. Maybe with NLP.
Because you already have a grammar, and it seems to me the grammar.
It's context sensitive. Bro.
Context sensitive.
It's not easy.
True, but that's like a compiled language in a way, right? So if you're able to compile things, you should be able to try to compile an HTTP request. If you compile successfully, then it meets the grammar, and otherwise you reject it. And if you want to be fault tolerant, you can reject it a word.
That would make the whole internet very slow, I guess, if you do that. I mean, every HTTP request will be.
It's true.
But if you're doing this for finding bugs, if you do it,
Yeah.
Every so often.
offline, I think it's fine. Another thing, I'll use the buzzword AI, maybe use AI. Who knows? Maybe it helps.
You always throw AI at the problem.
Be fine. All right, well, thanks very much.
I said one last one. Have you seen this in the wild? Is anyone trying any of these attacks?
In the wild, for real attacks, for Black Hat, there have been a couple of Black Hat talks where people have done this in the wild. So we know it can be done, but not at scale. So I'm not sure if anybody has done it. I actually asked my former student if this is being done at Akamai, but I do know that they see a lot of stuff. So, like apparently this is a thing now. So these C requests, everybody fixes something, but it's like a temporary fix, and then another issue is found.
Sure.
So I think it's happening in the lab.
Great.
All right, great.
Thank you.
Thanks a lot.